All right, well, good evening, everybody around the world studying for your professional maritime license or just interested in navigation in general. I'm Chris from Practical Navigator. Tonight we're going to talk about amplitudes of the sun. What is an amplitude of the sun, you might ask? Well, it's a great way for you to use the sun around the time of sunset and sunrise to measure the error in your magnetic or gyroscopic compass. So what you're going to want to do is picture yourself out at your favorite beach, right? And you're waiting there. You're waiting for sunrise or sunset. Let's say you're waiting for sunset. The sun is coming down towards the horizon and you're just waiting there. And we've all been doing a lot of waiting lately, especially with all this quarantine stuff going on. And I know personally I've been looking at a lot of YouTube, right? And so I came across a fellow YouTuber. He's a sailor friend of mine, Dustin, from Connecticut. And he's been doing some pretty cool stuff in quarantine. Making a skateboard, for instance.
So now we just added paint of red over here, and I think it looks sick.
I think it looks really sick too, Dustin. And so if you're able to, check out Dustin's channel, I put a link in the video description down below. He's got some great ideas on how to spend your time in quarantine while you're waiting for the sun to set. So a big shout out to my friend Dustin in Connecticut, a sailor friend of mine, while we talk about our sun setting here. Okay, so as we've been waiting, the sun has gotten closer and closer to the horizon. And if you imagine yourself on the equinox, right, that's when the sun is going to set exactly west, exactly due west, right? And that only happens a couple times a year. It happens on the equinox on the way north and the equinox on the way south as well. But most of the time, if you think about it, the sun is not setting exactly west. Right, it's going to set somewhere to the north of west or to the south of west, depending on the season. For instance, in the middle of summer in the northern hemisphere, the sun is going to set to its maximum difference to the north. It's going to travel up to the north and then start going back the other way. And this is what we call the solstice. That's Latin for the sun stands still. Right, so that's a good way to think about that. The sun stands still. It stops its movement and then heads back the other way. And then likewise in the northern hemisphere, in the winter, the sun has traveled all the way down to the southwest. And it stops there as well. So the solstice there. Right? So the difference between true west and the furthest distance it gets to the north and the furthest distance it gets towards the south can be measured as an amplitude. Right, so it's a number of degrees away from true west for sunset or true east for sunrise. All right, and if you can measure this, just like anything in navigation, if we can measure it, we know what there's going to be in degrees true, and we can compare that to what we see in our compass, which is degrees PSC, and then we can determine the compass error. So that's going to be our strategy here. And so Alex, as you say, yep, there's exactly right. There's 3 horizons, and that's going to be a key point that we talk about tonight is the different types of horizons that we see. So this is when we observe amplitude. What are we looking for? And more specifically, where exactly do we look? Well, the best way to do it, and exactly as Alex says, is there's different types of horizons out there, right? There's the visible horizon. That's the horizon that we can see out on the ocean or near a beach or something. And the best time to take this observation is not when the sun is on the visible horizon, but when it's about 2/3 of its own diameter above the visible horizon. Because at that point, it's on the celestial horizon. Right, and so because of atmospheric refraction, bend in the atmosphere, all that kind of stuff, all our math is going to work out best when this sun is on the celestial horizon. Right, and so the time to do that is when the sun is 2/3 of its own diameter above the visible horizon. So in essence, when it's kind of like that many suns above the horizon, take your measurement. Why is this important? Well, it's a very important question. In different parts of the world, for instance, if you're somebody that lives near the equator, the sun probably comes pretty much straight down towards the ocean and then sinks below it. It happens pretty quick. But if you're somebody that lives in a more higher latitude, like a northern or a southern latitude, you might see the sun taking this kind of angle towards the horizon, or in the southern hemisphere, sunset like that, right? And so if you don't take it at the right time, your measurement is going to be off a little bit. All right, so you want to make sure you take it at the right time. So the celestial horizon is the place that we want to make these observations. It makes our math a lot easier. However, we always see these, storm clouds out there in the distance, right? And so sometimes you have to wait until the sun is actually on the visible horizon. If you do that, we'll just have to make a little correction and we're going to be good as gold. All right. The other thing that we need to know about amplitudes kind of before we get into our first problem of the night is how we annotate these things. All right, so if we come up with an amplitude, that's west, and we come up with some type of amplitude, then we need to know how to name it. How do we know what number of degrees it is when we do our compass correction? The first thing you're going to want to do is name it based on the sunrise or the sunset. So if we're looking at a sunset, we're going to name this amplitude west, and then whatever the number is, let's say the amplitude comes out to be 5 degrees. We would name it 5 degrees, and then the suffix that we're going to name this is based on the declination of the sun. If you are unfamiliar with that, the declination of the sun is equivalent to the latitude of the sun. So if you were at the same declination as the sun, you would see the sun directly overhead. And we can get that information from the Nautical Almanac. Right? So we name it based on the declination. However, you can also name it based on the season. So in the northern hemisphere, in the summertime, the sun is north of west. We would give it an N for north. In the northern hemisphere, in the wintertime, the sun is to the south of west for sunset, and the opposite goes for sunrise. So this is best illustrated with an example, I would say. And I'm going to write up a couple of problems up here that we can solve. And if you're waiting for me to write something, you can maybe go check out Dustin's channel as well. I'll be back here in just a second. But our first problem is going to be on 11 January. Right, and it's 0655 zone time. That's our local watch time there. And our position is 24 degrees 30 minutes north and 122 degrees 02 minutes west. So that's our DR position, our dead reckoning position, latitude and longitude. We take a measurement, in the time of measurement comes out to be 14:55 GMT, Greenwich Mean Time, on the 11th of January. Right, so we've already converted this longitude and this zone time into GMT, but that's a skill in itself. If you want to refer back to previous live stream videos, we've talked a little bit about that. But converting your zone time into GMT is definitely a skill you're going to want to have going forward here. Other information that the problem might give you is that the variation in the local area is 11.6 degrees east. And we observe the sun on a compass bearing of 101 degrees per steering compass, PSC. And that's this kind of compass here. Although you might call this a magnetic compass, it's actually a steering compass. It's what we use to steer because it has not yet been corrected for deviation and variation. All right. Cool. So what we're going to do is we're going to need to organize our information and then go off on a quest to find something. And I think the most important thing we can do is probably take a look right at Böyük just to get started. And so I'm going to show you my electronic in the summer. Alex says, yeah. So depending on the northern hemisphere, southern hemisphere thing, everybody's got a different summer. That's exactly right. So I'm going to show you my trusty version of Böyük here. All right, and so in here is a table. It's going to be table 27, I believe, in this version of it. Every version is different. And if we zoom in on the table, we can see what type of information is required. So we definitely need our latitude, and we need the declination of the sun. So those are really the only two things we need to do in order to pull out an amplitude, and that's actually what we're after, right? So we'll put this table on hold just for now while we go on a quest for some more information, right? So it said we needed our declination and our latitude. Well, our latitude is given, but it's given in degrees and minutes, and we need it in degrees and decimals. So this turns out to be 24.5 degrees north. So we got our latitude. That's mission number one. Declination is a little trickier. It's Declination is going to be found in the Nautical Almanac. All right, so I think we've used the Nautical Almanac before in this little semester that we're running, but if not, I've got a couple of videos out there that describe the Nautical Almanac as well. All right, so for the Nautical Almanac, we're going to want to look on a date of 11 January. Here we are, 11 January. And our time was 14:55 GMT, Greenwich Mean Time. So on the 11th of January, 14:55 GMT. So the nice part about these type of problems is we don't really need to interpolate too much with our declination, because we're pretty much exactly at 1500. So let's just pull the time for 1500 out. So it's going to be south 21 degrees and 45 minutes. So I'll zoom in on there in case you don't have a Nautical Almanac lying around. But for 1500 hours, it's going to be south 21 and then 45 minutes. So if your time was not exactly near an hour, you could do some interpolation and pull out a corrected value. But this is going to be ours here, 21:45. All right, so let's write that down. Declination was 21, oops, not very clear, 21 degrees, 45 minutes south. And we also need that to be in terms of decimal degrees as well. So that's going to be equal to 21.75 degrees south declination. What we can do is we can go into Bowditch and we can pull out a value for the amplitude, the difference from true west or true east, depending on the time of year. So I'll get my Bowditch back out again. And I'm going to show you one version, one way to do it, and then I'll show you a quicker way as well. So in Bowditch, table 27, we'll zoom in, and we're looking for our latitude and our declination. So we said our declination was like 22. We're going to have to flip a couple pages. So here's 21.5, here's 22, here's a latitude of 20 and a latitude of 25. So just like a lot of things we do in celestial navigation, we'll have to interpolate these values or choose a value that's closest to what we're actually looking for. So we would land somewhere in this vicinity up here. So if you visually inspect this, somewhere in these four, we're much closer to a latitude of 25 than we are of 20. And we're much closer to, or we're actually halfway between a declination of 22.5 and 22. You can pull out a value, you can do some ratios if you want, or you can visually inspect it. But either way, if you came up with a value of 24 for your amplitude, that's good information to have, but we'll have to see, what are we going to do with that, right? What do we do with that? So, like that nomenclature that I talked about, the nomenclature is going to be, sunrise or sunset, and then it's going to be the declination from there. So our amplitude is 24 degrees. And are we at sunset or sunrise? Well, if we're at 0655 zone time and we observe the sun at 101 per compass, then this is going to clearly be a sunrise case. So we're going to be east 24. And then what you can do for the suffix is just simply choose the declination value or think about the season as well. Right? So this season is wintertime in the northern hemisphere. So clearly the sun is going to be south of west and south of east. So that's our declination nomenclature there. And so we can turn this into a real value. Well, if sunset is 270 and it's going to be sunrise is 090 degrees true, and we're south of it by 24 degrees, we have to add that value to it. All right, so that gets us 114 degrees true for sunrise. All right, and then the last step, if you happen to attend the session where we talked about compass problems, true vampires make dull companions at wakes, we can put all this information into our memory aid here. So this is going to be 114 degrees true. Just copying this here and cleaning up some space on the board. So true, variation, magnetic, deviation, and compass. We can fill in the information that we know and then solve for what we're looking for, which is the deviation of the compass. So this is what the problem has asked us to do. Our true value is 114 degrees true. Our variation was given as 11.6 degrees east. our compass was measured at 101 degrees PSC. And we can try and now find the deviation in the magnetic compass. If we do this out, just remember, if you're working your acronym this way, you're adding westerly things and subtracting easterly things. So rather than embarrass myself on camera, I'll use a calculator for this one. And I get 102.4 degrees magnetic. So what is the deviation in the compass? Well, it's the difference between this. It's 1.4 degrees. And then the question is it east? Is it west? That's the big thing, right? Well, remember, if we're adding things that are west going down, it looks like we subtract our answer here. So the true value is going to be 1.4 degrees east for the compass error there. So this is a typical question you're going to see on any level license from 200 tons to unlimited tons for the oceans navigation, or for the near coastal navigation, if you've got that type of test coming your way. So in summary, what we did, we write down all of our information that we know. We convert our latitude to decimal degrees. We find the declination of the sun in the nautical almanac, the naughtiest of almanacs, and we pull out an amplitude. Convert that amplitude to a degrees true by reasoning out sunrise and sunset, and then solving your true vampires make dull companions at wakes issue there, right? So one thing that always troubled me is that Adrian knows the can dead men vote twice at election version. So from here, can dead men vote twice at elections? If you go the other way, you add east. And definitely, you're exactly right, Adrian. If you use either memory aid, you're going to be good as gold, right? So what makes these things clunky for me is that whole step of trying to interpolate the amplitude value in there. And that becomes tough because you have to either do ratios, use a calculator, do some mental interpolation, that kind of thing. There's a quicker way to it. Right? There's a quicker way to it. So let's do the exact same example. But if you look in Bowditch, which is available in the tests that you have for Coast Guard exams, for US Coast Guard exams, there's a formula that pops out of it. And that is the sine of your amplitude is going to be equal to the sine of your declination over the cosine of your latitude. Right? And so we've already got latitude, we've already got declination. It's just a plug and chug into the formula. So this is maybe a quicker way to do it. You can either, one, memorize that formula, or two, look it up in Bowditch rather than using the tables. So if we were to do that, we can just plug the numbers right in. Right? So sine of A is going to be equal to the sine of 24.5 degrees over the wrong number. Sine of the declination, which is 21.75, over the cosine of the latitude, which is 24.5. So if you do the old calculator plug and chug thing there, you're going to end up with sine of A equal to 0.4072, the shift function on your calculator. Right? So say you had the 0.4072 answer in there. Here's the sine, the cosine, and the tangent functions. The reciprocals of them, the inverse functions, are just above them. So if you go shift and then sine, out pops your answer, 24 degrees. Right? So that's pretty magic, I think. That would give you your amplitude of 24 degrees, which is exactly what we got out of the table. And that's how the tables are constructed. So if you ever want to save time in your tables, you can definitely use the formula directly. Like I say, it's in Bowditch, so that's a handy thing. All right, why don't we do one more? One of Dustin's videos that I watched was top 4 pranks that you can play while you're in quarantine, and he had a really good one about making a broken TV prank. I thought it was pretty clever, so check that one out. All right, so on this one, we're on the 10th of February, and it's our position is 25 degrees, 32 minutes north, and 135 degrees, 15 minutes east. The sun was at a bearing of 109 degrees per steering compass, and the chronometer ended up being 0940:05. right? And we're gonna do something a little tricky here. Actually, I'm sorry, I have the chronometer time wrong. It's 2140. There we go. So we'll skip the part. We've already done chronometers and ETA problems in the past, so you can check out that video if you want. But sometimes the Coast Guard is going to give you a little trick with the chronometer, and you can just bypass it. Let's tackle latitude first. It's given as 25 degrees, 32 minutes. So I'm just going to say that's equal to 25.53 degrees north. We got our latitude. So that's perfect. Declination, that's going to come from the Nautical Almanac. So we're going to go to the Nautical Almanac for a day of 10 February. We'll go take a look at that. So here's 10 February. Here's the 9th, here's the 10th. We'll zoom in on that. And our time was 2140. Right, so if we look at 2100, our declination is south 14, 9.6. Right, for the sun's declination. All right, so 2140 is our time. So let's see, we're kind of closer to 22 here for the declination. So there's a couple ways we can do this. We can mentally interpolate, or we can use what's known down here as the D number, which is the hourly change in declination, and we can solve it that way. So let's be as precise as we can on this one. So our time was 2140. 05 GMT. So the declination for 21 is south 14, 9.6. Right, and the D number is 0.8. And it looks like the declination is decreasing as time goes by. So that makes it a negative. Everybody's got their own method of notating this stuff. That's mine. The negatives on top kind of thing. Right, so what we need to do then is go into the increments and corrections pages in the Nautical Almanac, which is towards the back here, for a time of 40 minutes. And then we look up our D number here. Right, the D number. And so our D number was negative 0.8, so our correction is 0.5. I've got a couple other videos about how this works, the Nautical Almanac and stuff, but our correction is going to be 0.5, negative 0.5. That makes our total declination south 14 degrees, 09.1, and we can turn that into decimals as well. So 09.1 divided by 60 gets you south 14.2 degrees declination. So we got our latitude, we got our declination. Type in our formula, or use the tables in Bowditch if we want. But we'll go with the formula for this one. All right, so the sine of our amplitude is equal to our cosine latitude, sine declination. So we're plugging in numbers here. The sine of your amplitude equals the sine of your declination, 14.2, over the cosine of your latitude, 25.53. So your sine of your amplitude, rather than watch me type numbers into the computer, I came up with 0.2769 earlier. So we'll go 0.2769 shift sine to get our value of 16 degrees. So amplitude is 16 degrees. So what's that telling us? Well, this is a case of sunrise. So normally the sun would be right to the east, right? And we're deviating from it 16 degrees, either that way or that way, right? 16 degrees. So we got to figure out which is which. So amplitude is 16. And what is the prefix? The prefix goes with the sunrise or the sunset. So for sunrise, it's east, 16 degrees. And then the season or the declination matches for the suffix there. So east, 16 degrees south. In other words, 90 degrees and then 16 degrees south of it. All right, so that gives you 90 plus 16, or 106 degrees. True. You've got your true value then. Yeah, increments and corrections, Adrian, is a tough thing. It takes up a lot of time. So that's the thing about celestial navigation problems, is they're actually not too hard, but you have to spend a lot of time working on all the details, is what makes it challenging for you. Okay, so our true bearing is 106. So I'm going to erase some of this extraneous stuff here. So 106 degrees true is what they were looking for. So if we do, let's do your other version there. Can dead men vote twice at elections? We're going that way, we're going to add east. So 106 degrees true. Our compass course was 109 PSC. Oh, I think I forgot to write it down, but the variation was given in the problem as 4.5 west. All right, so we're looking for the deviation in the compass there. So if we're going this way, we're going to add west things. So 106 plus 4.5 gets you 110.5 degrees. Magnetic. And then what's the difference? What's the difference? That's going to give us our answer for our deviation. So it looks like it's 1.5 degrees. And then is it east? Is it west? Well, if we're going this way, we add west things. So it looks like we subtract in this case to make it 1.5 degrees east. All right, so that's a second problem for you. And we're doing good on time. So I'll just talk briefly about the third problem that we're going to do and the difference between them. So we'll go from there. So I mentioned that we want to take this measurement when the sun is 2/3 of its own diameter above the visible horizon. Then it's on the celestial horizon. But if we miss, for whatever reason, and the sun is on the visible horizon, right, we can take this measurement and we can apply a correction to it. So the correction is the next table in Bowditch, right? And so as an example, let's say we came up with a declination of south 11 degrees 08.0. We looked in the Nautical Almanac. I've shown you that before. We don't have to spend time on it. And we had a latitude of south 11.1 degrees. Right? Oh, I'm sorry, our latitude is south 21.9 degrees. Writing down the wrong numbers here. So this becomes 11.1 degrees. So I skipped a couple steps here just so we can focus on the point of the problem here. These are the two numbers that we solve for. And we need to get an amplitude out, right? So we can do, the formula, or we can look in Bowditch. And what if we say our amplitude comes out to be 11.9 degrees, and then we turn that into west 11.9, south, and therefore 258.1 degrees true. So these are all the steps that we've done in a previous problem. We've done two of them so far tonight, so I won't waste your time on that. However, if we didn't observe it on the celestial horizon when it's 2/3 of its own diameter above the visible horizon, we have to make a little correction to it, right? A correction. And so what we're going to want to do is go into this table over here, which is table 23 in Bowditch. It's a correction of amplitude. So it depends on your version, I guess I should say. My electronic version, it's table 23. My paper version, it's table 29, I think. What you do is you look for a little correction. So just like before, what's our declination? Declination is 11.1. So it's kind of right in the middle here. And our latitude is 22 degrees. So it looks like our correction is going to be somewhere in this vicinity of 0.3 or so. So it's just a little tweak that we make. Our correction equals 0.3. So these corrections are actually tricky. So what you do is you're not going to apply this correction to this, right? Because that's true bearings that we calculated. We're going to apply this correction to what we actually observed. It's a measured bearing. If you read the instructions in the table, that's a key distinction, right? So let's say we had measured, I think 256 was what they said. So 256 degrees PSC is what we measured. You're going to make this correction to that, right? And the way that you do it is you do it what's called away from the elevated pole. So our ship is in the southern hemisphere, and we're looking at sunset. We're looking this way. So this is the elevated pole, the closest pole to you. So you have to apply the correction away from it. So our total PSC is going to be 256.3 degrees, right? And so then you've got your compass course, you've got your true course. You can put all this into the True Vampires thing, just like normal. Or the Can Dead Men Vote Twice thing. This one is going to go here, 256.3. This one's going to go here, 258.1. True. And if the problem earlier, I neglected to tell you, but maybe it was 2 degrees east, we can solve for our deviation just like we have been before. So 256.1 magnetic. And what does that make it? It makes it 0.2 degrees. We're adding west in this case, right? So it makes it 0.2 degrees west. Unless I made a math error, that's where it's going to come out. So the point to this little exercise was using the correction table in Böyük. Right? So sometimes if you want to get into the weeds on this stuff, in real life, you know, it's not ever really going to be a significant correction. But on the other hand, if you're doing this, you're doing it to correct your compass. So you might as well be as accurate as you can. So table 23 in one version of Böyük, table 28, 29 in the other one, I think it was, for the corrections. For Coast Guard problems on US exams, you're going to see mostly the first type on the celestial horizon, but they'll probably always throw a visible horizon one on you as well to make sure that you can make the corrections on it. So if you do make those corrections, you'll end up with the exact right answer. In real life, it's something you can probably forego. All right, so I'll leave it there for tonight. That's what we're looking to do is amplitudes tonight. We got a few more weeks left in this Thursday night semester. I'm thinking probably 3 or 4 more sessions we'll do, so tune in for these if you want. Always you can go back and look at the previous videos if you're studying for your exam. We're covering a majority of the topics you can see on an oceans or near coastal nav exam. So don't forget to check out my friend Dustin's site. It's in the link in the video description below, and I'll plan to see you next time. All right, thanks for your attention, and have a good night.